So this is section 3.1, maximum and minimum values. A lot of the beginning of chapter 3 is going to be talking about graphing functions. And we know a lot about graphing functions from pre-calculus, college algebra and trig, those sorts of things. We know things about asymptotes and we know things about intercepts. And we're going to bring all those things back and then combine it with the idea of calculus and doing derivatives. So in this section, we're going to talk about the idea of, on a graph, maximum and minimum values. So first we're going to mention the idea of an absolute maximum. And an absolute maximum on a graph is if you are on some sort of domain, whatever that is for some function, you have a maximum. And that maximum is a y value. And it occurs if every other value is smaller than that. Every other y value is smaller because that value is the biggest, the highest. Now, obviously, highest is relative depending on your function. Conversely, you'd have a minimum, and it's called an absolute minimum, if on a domain, every single other value, y value, is higher or, above that value. And that's what it means here. So you have the value at some x value, in this case called c. And so it creates some y value that is lower. So this value, this y value, is less than or equal to all other y values on that domain. And those y values are called the absolute mins and absolute maxes. So if you want, you can pause and take a look at this graph that we have here and see if you can come up what is the absolute maximum value and what is the absolute minimum value on this domain. So on this domain, the maximum value is q and the minimum value is r. Okay? And that's whatever that y value is. We're just kind of looking at a graph here. Now understand that if this line had come up, if this function was, say, a little bit taller, say it went up to here, that the maximum value would actually be right here and not q, because it is literally saying that on this domain, and if we start over here at A and we end at B, and of course I kind of extended mine a little bit there, but the idea is it is the highest or the lowest value on that domain. That's what it means to say absolute max or min. We also have the idea of a local or relative maximum or local or relative minimum. And of course, we're using our very mathy notation here. But it's telling us that we have a local or relative maximum or minimum when that y value is higher or lower, depending on maximum or minimum. For all x, notice we're going to say near c. Near c. So that simply means that if a function goes up and comes back down, you're going to have a local or relative maximum. If that function comes down and then goes back up, down there, you're going to have a local or relative minimum. And so you could have an infinite number. You could have an infinite number of local or relative maximums or minimums on a function. So if you consider the function sine x, that would be an example of a function that, if you're thinking of its domain, which is actually negative infinity to infinity, you have an infinite number of relative maximums and minimums because this function just keeps having a high point and then a low point and a high point and a low point and a high point and a low point. And that's what it means to say local or relative max or min. So take a look at the picture that you have above and see if you can determine any local maximums, local minimums, and understand that something can be an absolute max or min and can also be a local or relative max or min. It's just by definition that any value around it is either lower if you have a maximum or larger, higher if you have a minimum. So go ahead and pause and see if you can come up with those values. Local maximums are going to be Q and S. So if you take a look at the graph, you can see here all the values around and near Q are actually smaller y values. The same here. It's not saying, when we talk about near, we're just talking about these values very close to S, those y values. And those are all below that, whatever the y value is there at S. And conversely, we have 3 values for local mins. So here you have a local min, here you have a local min, and here you have a local min. So I'll put those back on the other one. P, R, and T. Okay. Now, notice the definition does not include endpoints. So there's a big difference. When we talk about absolute max, we're talking about on some finite domain. We're talking about on domain D. Whereas when we're talking about local or relative minimum, it could be any domain, it could be anywhere. When we talk about an absolute, we want to be able to say, like, you know, if the function is a polynomial and it goes, you know, it comes from negative infinity and then does something like this and goes up to infinity, you're not going to be able to find an absolute maximum or minimum because that function keeps going down to negative infinity and it keeps going up to infinity. There's never a finite y value up here and there's never a finite y value down here. So you do need that specific domain to find your absolute maxes and mins. So our extreme value theorem, also known as the EVT, says that if you have a function that is continuous on a closed domain, then it must obtain some sort of absolute maximum and some sort of absolute minimum on that domain. And you just have to think about it. It's continuous. So it might go up and come back down and go back up. It might not do that. So let me show a couple examples here. So say you just have a basic function that like just continues to increase, you know, something like this. And let me see if I can, okay, I'm just trying to get a good point here. So just bear with me on this picture. But the idea here is this function continues to increase the whole time on its domain. So if we think about its domain here as being from 0 to 4, and you are asked to find what are the absolute maxes and mins, well, in this case, it has a minimum of what y value, and that occurs where? And it has a maximum of what y value, and that occurs at what x value. So understand that in a case like this, the absolute min and max are occurring at the endpoints. And that's all that there is. However, there's definitely a situation that you could incur that would have a situation, it's going to be something, you know, different options here, but I'll just show you one example. So you could have something that comes down, for example, maybe hits here, goes back up, you know, and then at some point comes back down, something like this. Again, I'm just trying to come up with some good points here to make our lives a little bit easier. Let me do that. Okay, so if we have a function like this, notice it's not always increasing, it's not always decreasing. So when we think about the domain, in this case from 0 to 5, it is continuous. So it has that absolute min, that's going to be 0 because that's the lowest y value that we see, and that occurs at x equals 2. You can probably see the maximum is going to be 2, and that occurs at x equals 4. So in this case, we have a minimum here, a maximum here, and neither one of those things are the endpoints. So it could occur at the endpoints, or it could occur where, as you can see, and this is hopefully what kind of the big idea here is with the derivative, is you should notice that that's a very specific, that's a place where the derivative is a very specific number, where the slope of the tangent line would be a very specific number. And because of that, those are the kinds of things we're going to have to check when we're asked to find absolute max or min. So we'll do an example of that soon. Okay, so now we have Fermat's theorem. And I don't know if you've heard of Fermat, but he has many, many theorems, and he has many famous theorems. So if f has a local maximum or minimum at c, and f prime of c exists, so the derivative exists and it has a local max or min there, then we're told something. So it applies, let me do a little graph for you here. It applies, for example, if you were to have, your graph comes down, it comes back up, and it goes like somewhere. Okay. Remember, this is local here. This is local, so my function can start, it can keep going, it doesn't matter. I don't need to be thinking about a finite domain. But you can imagine that there is a value right here, I guess I didn't do that as perfect as I had hoped, where you have a local maximum. Around it, all the values are lower. Okay. Here you have a local minimum. All the values around it are higher. Notice as well that it changes, the function changes from decreasing to increasing and then increasing back down to decreasing. So we have a local max or min, and the derivative exists because this function is continuous, and you can see that it doesn't have any sharp curves or cusps or anything. So what we want to really see here is that the derivative at that value has to equal, some of you are probably already thinking about it, 0. And that's because if we were to think about a tangent line here, the slope of that tangent line would be 0. If we thought about a tangent line here, bear with me on my picture, we'd have a tangent line that has slope 0. So this is why this is really important, because if we can take a function that we don't have a graph of and we can find the places where it's equal to 0, that can help us to find local mins and local maxes. So when does Fermat's theorem not apply? An example would be our very popular, that we've seen many times, the absolute value function. Y equals absolute value of x. Now in a case like this, we do have a minimum of 0 at x equals 0. Not particularly exciting. But f prime of 0 does not exist. There is not an actual value there that we know that the derivative, because it's a sharp corner, does not exist. So what I want you to see is, because this does not exist, we know that that derivative at that point is not in fact 0. So you've got to be smooth and continuous. You've got to have something nice here where that you have the derivative is existing and you can see that you have a local min or max. Then you have that the derivative is 0. So that number c, and this will come back later, is what's called a critical number for your function. And that critical number is going to occur wherever the derivative is 0 or the derivative doesn't exist, because it's an important value. It's going to tell you something. So the big point of this section is to find absolute extreme values. And the way that we do that is we find the values of the function at the critical numbers. So that would be anywhere where the derivative is 0, anywhere where the derivative doesn't exist. Then we'd find the values of f at the end points. And by doing that, that's going to tell us all the y values that are essentially important to us to be able to determine absolute max and absolute min. So then we just compare the values and say, well, which one's the largest and which one is the smallest? And that's our absolute max, absolute min. So let's do a couple examples and we'll see what happens. So on the version of my paper here, I've actually done the graph for you so you can see it. Yours is going to be scaled a little bit different, but I did want to show you what a larger version is. So for something like this is a polynomial. We know this. This is smooth and continuous on its, domain, which is all real numbers. But we're only going to be talking about from 0 to 1. So we just want to find out on that domain, just from 0 to 1, what is the largest y value, what's the highest, largest y value, and what is the smallest. And the whole idea is to do this without the graph, but I'm trying to give you a little bit more right now just due to the fact that I can't change over to Desmos when I use a program like this to record. So for your graph, you just need that 0 to 1. So you can probably already see it here. So you can see that you have one endpoint, you have another endpoint, and then you have this value here, which is quite low. And that's actually lower than your left-hand endpoint. Maybe I should go like this because you guys are backwards. Left-hand endpoint. So the way that we find that without graphing, because we won't always have a graph, is the first thing we have to do is take the derivative. So the derivative of the function, go ahead and do that. You can pause if you want, take the derivative. And you get the derivative. The derivative is defined everywhere. There's no issue. And so we don't have any kind of weird cusps or anything like that, any corners on a polynomial or its derivative. And so we just need to find out when is it equal to 0, because that's when we're going to have a tangent line that's equal to 0, which is going to indicate a possible maximum or minimum. So we're going to factor this. And that's going to give us either x equals 1/3 or x equals -1. So I'm using the zero product or zero factor property there to give me those two values. Now, obviously a big thing to understand is that this value, -1, is not in our interval. It's not part of this domain that we're talking about for this function. So you don't have to worry about it. Just don't worry. It can't be one of the extreme values. It can't be an absolute max or an absolute min because it is not in your function. Now you can see, you might be seeing, well, I see it over here because my graph has it, but it's not in our domain. So yes, it would be important to us if we had a different domain, but we don't. So x equals 1/3 is going to be important. So we do need to find f of 1/3. We need to find what that y value is. You can see it on the graph, but we need to find out what it is. So we're going to have 1/3 cubed. We're going to have 1/3 squared, and we're going to subtract 1/3 from that. And we're going to see what we get. Obviously, you're always welcome to do that. I get a -5/27. Remember, numbers are not always so pretty. So that is the first step, and I'm following the steps just from right above you. I'm not like looking up at the sky here, but above you on your notes, you have the 3 steps. So we checked our critical values. The only one we care about is the f of 1/3 equals -5/27. And then what we have to do is we have to check the endpoints. We need to find f of 0, and we need to find f of 1, because these are the only other 2 places where you might have your highest value or your lowest value. So we plug those in, and f of 0, you can see, would be 0 cubed plus 0 squared minus 0. Very not exciting. And plugging in 1 is going to give us 1 cubed, 1 squared minus 1. And we can see that that's going to give us 1. So what we have here is 3 different y values. And that's all we're looking at here. That's all we're caring about at this point in time. So we have a y value of -5/27, a y value of 0, a y value of 1. And now we just have to decide which of those is the largest number and which is the smallest. So we can see we are going to have an absolute minimum at the smallest y value, -5/27. And what might be better for me to write would be that the minimum value, so I'll use the word of, that's better. So a minimum value of -5/27 at x equals 1/3, because that's the smallest, lowest y value we have. And we have an absolute max of, and then we just want the largest y value, which is 1, at x equals 1. So again, we can see this on the graph. We can see that the lowest value is occurring at that fractional part, 1/3 between 0 and 1, and that the highest value is 1 at 1. And that's all that this is. Those are the extreme values for that function on this domain, and that's all you have to do. But do focus on making sure that your answers look like this. The absolute max or min is not a point, it is a y value. It is an f of x. And so my absolute max and absolute min here are y values that occur at a certain x value. So that's a key thing to know. So let's look at the last problem now. This one's not as pretty. Sorry for that, but obviously we know functions are not always pretty. So notice I've done the graph here for you just so that you can see it, but that's just to help for clarity. We want to understand that you don't need it, but it is there. And it's going to help us to kind of see things. In this case, being asked the extreme values is being asked to find the absolute max, absolute min. And you can see in this case with the endpoints that you have that those endpoints are not really occurring at anywhere special. We're still going to check them because we need to, but we really can already see due to the graph that I'm giving you that we have an absolute value here and that we have an absolute value up here. And so really what we're going to do is try to find out what those values are and where they occur. So first thing we need to do is we need to take our derivative. So we need f prime of x. And what I'm going to do is I am going to need the product rule. Yeah, I need the product rule here. So I'm going to, and you can do this a couple different ways because you know what's the sign in between the product rule terms. I'm going to take the derivative of x and I'm going to multiply it by the square root of 9 minus x squared. And then I'm going to add to that x times the derivative of 9 minus x squared, square root of that. So 9 minus x squared to the 1/2 is going to be 1/2 9 minus x squared negative 1/2 times a negative 2x. And I really can't say this enough, but you're always welcome to pause and find answers yourself to help with your understanding. So the derivative of this, I'm going to do a couple things here. So we have 9 minus x squared. I'm going to simplify x and 1/2 and negative 2x. So that's going to give me a negative x squared. And then my denominator here is going to be the square root of 9 minus x squared. Now, the reason that kind of I take a moment with this is because I want you to see that we need to find out when this is 0. And you might look at it and be like, well, I don't, not sure. And totally understandable. However, there is one thing that you can do. Anytime you have one fraction and you have something that doesn't have a fraction, you understand that you can give both of these fractions the same denominator, which means giving the first term a square root of 9 minus x squared. But if I give the first term the square root of 9 minus x squared in the denominator, I need to multiply the numerator by that as well. But since the numerator is the square root of 9 minus x squared, I'm doing 9 minus x squared squared, the square root of that squared. So I just get 9 minus x squared. Then I'm going to add negative x squared, and then I'm going to have the square root of 9 minus x squared here. So my second term is the same because it has the common denominator. And then I can combine those to get 9 minus 2x squared over the square root of 9 minus x squared. Now the reason that this is so important is because we are trying to find out when does that thing equal 0, because that's where we'll have a critical number, which is where we may have an absolute max or absolute min. And here is really one of the key things of anytime you're setting a fraction equal to 0. Anytime you set a fraction equal to 0, understand that the only way for a fraction to equal 0 is if the numerator is equal to 0. You're not even worried about the denominator. You have to think about it in terms of when is there a place where the denominator would be 0, because you could have, that's a critical number, because if the derivative is undefined, that's important. But for the derivative to be equal to 0, it can only be the numerator. So we can kind of see that this is not going to be the prettiest values. We can see that on the graph as well. But we have x squared equals 9 halves, and that's going to give us, I'm just going to flip it, x equals plus or minus the square root of 9 over 2, which is plus or minus 3 over root 2, which if you want is plus or minus 3 root 2 over 2 if we rationalize it. So it's not surprising. We can see from our graph that there are two values here where we have a high point and a low point, and we see the symmetry that's happening as well. So we're not surprised by that. Now, the what we see is that the f prime of x, where the derivative does not exist, would be when the denominator is equal to 0, and that's plus or minus 3. That's also the endpoints, so we're checking those anyway because the derivative doesn't exist there, as you can see, because that's where the domain ends. It's not a sharp cusp or a corner or anything like that. So here we have this, and so now we're basically just checking all these values and then we're just seeing which ones are the highest and the lowest. So let me find f of 3 root 2 over 2. So understand this is going to go back into your original function. That is what it's finding. You're finding the y value, and the y value is from the original function, not from the derivative. The derivative is telling you the slope. So you would need to find both of these values, negative 3 root 2 over 2. So you can plug them in and do the work on them. You do end up, I'm just going to show what value you get out, but you would go 9 minus that thing squared, take the square root of it, and then multiply it by your x, 3 root 2 over 2. And if you do that, you're going to get 9 halves, which is 4.5. And you're probably not going to be surprised to find out that when you do the negative 3 root 2 over 2, you're going to get negative 9 halves, or negative 4.5. So notice the symmetry there. So then we're checking our endpoints, which we're checking because our derivative is undefined there anyway. But f of negative 3 is going to give us 0. You can see that from the square root piece, that 9 minus something squared, that is 9, is going to give you 0. And the same with 3 is going to give you 0. So in this case, and we can see this from the picture, but again, you don't need the picture, the absolute min, so we have an absolute min of, we want the smallest y value. We can see that that's negative 4.5, and that occurs at the x equals 3 root 2 over 2. And that we have an, sorry, that's going to be at negative root 3 root 2 over 2. And then an absolute max of 4.5 at that positive value, x equals 3 root 2 over 2. So let me just quickly go over the steps, and then we're done with 3.1. You're going to, when you're asked to find extreme values, absolute max and absolute min, you take your derivative and you find out where the derivative is 0 or undefined. And you find the y values at those points. Then you find the values at your endpoints, the y values at your endpoints. And then you just compare everything. What is giving you the largest y value? What is giving you the smallest? And that's going to tell you your absolute max and absolute min. And that is section 3.1.